here I'm going to have done is to introduce a little bit more information about this, and that one is we can look at here by these equations. Again, using the eccentricity vectors. Then I'm going to try is to take the inner product of the E. So this one basically is E squared. Okay, so that one can be done by this. We simply manipulate this one and quickly, so that is 1 mu square and V dot H and minus mu over R dot V cross H minus mu R vectors. Okay. And again, this one, if we can expand it, and let me do expand, and then I will directly give you the result. So this one is V cross H dot V cross H. Right now I'm kind of expanding the terms. Minus 2 mu R and dot V cross H plus 1. Okay, after expanding, and then again, here we can utilize the old tricks, and okay, let me do this quickly. So this term basically equal to can be we can use the old information, and that is equal to this one. Okay, and here we can look up the geometry textbook, and I found that one we can put into here. And because V is the H is input, H is the so this is the orbital plane, and this is the R, and this is the velocity V, and H is the vectors out of the plane. So that means the H dot V, this term is always equal to 0. Again, this is the orbital plane, and this is the direction pointing to H. So that making the second term equal to 0. Okay? And for this one, again, we have the previous done that before. So that is equal to R cross V dot H. So this term is H squared. Okay, so now we can quickly have this information. So for this equation, that can be described by therefore, and that one is equal to mu square and V square H square minus mu R and H square plus 1. So we rearrange the whole things. So left hand side equal to E squared. So therefore, E squared minus 1 equal to those things. So let me skip that part. So therefore, 1 minus E squared equal to H. I rearrange the terms quickly. Okay, how can we utilize these equations? And again, let me explain a little bit more. So let me rewrite that equation through here. So 1 minus E squared equal to H squared over mu, and 2 over R minus V squared over mu. In these equations, what we have is this H squared over mu. That is our definition of the P, the parameters we seen before just a few minutes ago. Okay. And for these equations, and also for all the orbits, and as long as is the mechanical energy is fixed, That means eccentricity must be a constant. Okay. So therefore, the left-hand side is a constant, which means the whole equation is a constant. And again, the P is relating to the magnitude of the angular momentum. So which means what I want to say is this term is a constant. This term is a constant. So therefore, this term must be a constant. Okay, so that means here the 2 over r minus v squared speed squared over mu. This term is a constant. Why not we give a definition? This definition is defined by, don't feel weird, I just follow the textbook, give you the best way to read the textbook. 1 over a. You might ask me before asking why not you define a constant is in the inverse, not directly. I just follow the people's the learning curve. I would say learning curve. Okay. And actually, defining this is not arbitrary. So here the A is defined as the semi-major. Okay. So what is a semi-major? For example, so in terms of an elliptic orbit, so this is the focus to focus in an elliptic orbit. And so say if we impose the geometry here, so this is the longest, sorry, my drawing is not so perfect. This is the longest, the axis, the shortest axis. So this is given by A. We call the semi-major axis. Okay, and this one is called the B, and semi-minor. Okay, and here later we will have a review of the conic sections. This one is called C. C is the distance of the focus. Okay. So therefore, here we have information. So to build it up, is we can have this. P can be described by EA minus E squared. So that is a second useful information, and you can use. So that is the first for the first portion of the note, and to give to you. And also, so let me say this is the note 1 here. And the second note is this, and again we recall our mechanical energy is defined by V squared minus mu over r, right? So this is the mechanical energy we've seen before. That is the specific mechanical energy. And then compare the right-hand side of this equation to the definition of A. If you look at that carefully, sorry, make you bored. You can see this one actually is equal to. Again, if you compare this term with this one and do a little bit manipulations, then you can see actually E is equal to minus mu divided by 2A. So here I add it up here. So this equation we're going to use. Mechanical energy equal to minus mu over 2A. And those kind of, I boxed those equations because I know those will be used a lot and in the exercise, so that's going to be highlighted here. And from this equation, you can see the E equal to minus mu A. So from here you can see, say, I have, if we have an orbit here, so say this is the bigger orbit, and say this is the Earth. And the second orbit, and say that can be, say, like this. So let me say this is, not this one. So for this orbit, it has the semi-major, the axis, say, A2. And for this orbit, it has the semi-major axis, A1. So for example, A1 is greater than A2. Okay? So which means this orbit is larger than the blue one. So who can tell me, in terms of mechanical energy, which one is larger, which is more negative? We have two orbits. Which orbit has more negative mechanical energy? Can you see from here? Mechanical energy is this. The smaller the value of the A, the more negative the E. Right? So yeah, so the blue one has more negative mechanical energy. So which means the blue one has a smaller mechanical energy. So that kind of fit into our common sense. If you have, I just erased it, we have the drawing this curve. And then if you label the energy, then the higher the energy, you have a wider range of the orbit space you can approach. So here, in terms of calculations, we can verify gradually piece by piece what we see. Okay. The third one, I forgot, but the third one should be made here, but that's okay. I can make the third one here. For the third one is this, let us revisit this equation, the second equation, P equal to A times 1 minus E squared. And here I'm going to prepare ourselves to the next section, or next two sections here. So we know the P, again, what is P? P is called the parameters by definitions. By definition, P is relating to the angular momentum square. So, which means this term is always positive. And E is the eccentricity vectors. Eccentricity vectors can be let me make it one. So say when E is less than 1, greater than 0, then this term is positive. So corresponding to here, the A is positive. So therefore here the A is positive. Okay? And because this is always positive, so say if we have E is greater than 1, then this term is negative or less than 0, right? So that means A is negative or 0. So which means when we go to the scenario next time or next week, when we talk about the scenario when E is positive or 0, then all the terms of the semi-major become negative. And I would remind you about the point here once we go to there. And don't feel weird to that point. And that is when many years ago, when I first touched this topic, I just feel weird. Why in geometry they use a negative value to measure measure the distance? I feel so weird, but actually that comes up from here. So I give you a head up here, and probably you don't have a good feeling, but that's okay. We keep this in mind. And